Hello everyone, myself Mohsin, and we are starting today a polymer chapter from your class 12. See, and this chapter is being omitted from the CBSE exams. So we are currently looking at the uh, polymer chapter with respect to IIT JEE exam, JEE means exam. So we will start polymers. You will find at least one question from the mains exam from the polymer chapter, and it is a very easy chapter, and you will find a very easy question from it. Basically, you will get a question regarding the type of polymer and the monomer. So let's start the polymer. So polymer are basically made up of small units, which are known as monomer. When we take large number of monomeric unit, suppose I am taking n number of monomeric unit, these monomeric unit combine together to produce a long chain compound that is known as polymer. So in polymer, what we have monomer, and monomer combines together to give polymeric in a large scale. So the polymer word arises from the Greek word. It means poly means many and mer means unit or part. So polymer means many units or many parts. The term polymer defined as the very large molecule having molecular mass 10 to the power 3 to 10 to the power 7. Basically, when we combine small units with a lesser mass, they give you a large unit that is a very large molecule, which basically consists of 10 to the power 3 to 10 to the power 7 atomic mass unit. Polymer are also termed as macromolecule. There are micromolecules, which are less in size and we can say mass, and macromolecules which are bigger molecule, very large molecule. Polymers are formed by the repeating structure unit on a large scale, that is basically monomer. The repeating structure unit are derived from some simple and reactive molecule known as monomer and are linked to each other by covalent bond. So basically monomers combine together to produce a polymer, and the bond between the monomeric unit is covalent bond. So this is the basic idea of the polymer. And now we will discuss polymer and their classification. So the study of polymers that are formed by the monomer is known as the polymerization. So when we are forming a polymer by the combination of monomer, so we are studying the polymerization. The process is known as polymerization. So now we are classifying the polymer based on, first classification is based on the origin, from where we get the polymer. So here we have first natural polymers. Natural polymers are obtained from the natural sources like plant and animals. Polymers found in plants and animals are natural polymers. Examples are like protein, cellulose, starch, resins, and rubber are the example of the polymers which are found in plants and animals. Like this is the structure of cellulose. So cellulose is a natural polymer. Next, we have synthetic polymers. Synthetic polymers are also known as artificial polymer, which are man-made. These are synthesized in the laboratory. So these polymers are prepared in the laboratory. Polythene, nylon 6s, Dacron, polyacrylonitrile, PAN are the example of the synthetic polymers, which are prepared in the laboratory. You can see the example of ethene. A polymer which we get from the ethene is polyethene. So we are combining n units of CH2 double bond CH2. We have taken n units of ethene and we are combining it to get polyethene. So polyethylene is a synthetic polymer. Semi-synthetic polymer are those polymer basically which are modified by the mixing of natural polymer and some chemical reaction occurs during it. So these are basically the polymers which are found in nature and then we have modified them. Those are known as semi-synthetic polymer. Polymer are found plants and animal, then modified in laboratory are termed as semi-synthetic polymer. Cellulose acetate, rayon, or cellulose nitrate are the example. You can check here. So if you see in cellulose, basically you have OH group in cellulose. And in cellulose acetate, what we have did, we have replaced the OH group by the acetate group. So cellulose is the natural polymer. And when we have replaced OH group of cellulose by the acetate group, it will give us cellulose acetate, which is a semi-synthetic polymer. So we have three types of polymer: natural polymers, which are found from the plants and animals like protein, cellulose, starch, resins, and rubbers. We have synthetic polymers, which are prepared in the laboratory, like polyethylene, nylon 6,6, dacron, and polyacrylonitrile. And then we have semi-synthetic polymer, the natural polymer which we have synthesized. Okay, so moving on, next category of polymer is based on the structure of polymer. So we have linear polymers. What are linear polymers? Linear polymers are basically made up of long straight chain. In linear polymer, we will find long straight chains. Examples are high density polyethylene and polyvinyl chloride, which is also known as PVC. So you will find monomers are grouped together in a chain. So this is the structure look like. These are the two chains of linear polymer. Next, we have branch chain polymer. In branch chain polymer, what happens? In linear chain, we have branching in that. So the linear chain which have some branches. Example is low density polythene, LDP is known as. So you can see this in a chain, we are having branching. So when we have branching in a chain, so we call them as branch chain polymer. And the next one, we have cross-linked or network polymer. Cross-linked or network polymer. In this, what happens? The chains are connected with the chains have the connection in between them. So those kind of polymer are termed as cross-linked or network polymer. These are usually found from the bifunctional and trifunctional monomeric and contains strong covalent bond between various linear chains. So basically you will have linear chain and linear chain will connected through the bifunctional or trifunctional group. Examples are bakelite and melamine. It looks like this. Chains are connected with each other with bond. So it gives us cross-link or network polymer. This is known as cross-link or network polymer. So on the basis of the structure, we have three types of polymer: linear, branch, and cross-link. In linear chain, we have simple chain joined together of monomer. In branching, we have in a linear chain some branching. And cross-link, the chains are connected with each other by the bonds. So this is the classification based on this structure. Moving on to the next classification. The next classification is based on the mode of polymerization, how we are going to produce the polymer. That is the next classification. So on that basis, we have two types of polymer. First one is addition polymerization or addition polymers. Type of polymers which is known as addition polymers. In addition polymer, the addition polymer are formed by the repeated addition of monomer molecule possessing double or triple bond. So this is important here. The addition polymers are formed by the compounds or monomers which are having double or triple bond. For example, polyethylene, buna S and buna N are the example of addition polymer. For example, you can see we are having ethene molecule which consists of a double bond, and when we have polymerize it, we will get polyethylene. So double bond break and we get a n number unit combined together, that is monomer of the polymer of polymer. So addition polymer, we should have double or triple bond in the monomeric unit. Next, we have condensation polymer. So condensation polymer we get by the condensation of polymers. Here, what happens? We will have a functional group. In that functional group will react and produce a molecule, and that molecule polymerize to give polymer. So in this type of polymer, in condensation polymer, what happens? There is elimination of some small molecules, such as water, alcohol, or hydrogen chloride. So the removal must be there. Water, alcohol, or hydrogen chloride is removed in these type of polymer. For example, nylon 66 and terylene are the example. Let's say by giving the chemical equation. So we have two monomeric unit, hexamethylene diamine NH2CH26 NH2 and adipic acid CH2COOH on the both the side of the molecule. So what happens? Water molecule will be removed from the hexamethylene diamine and adipic acid by the condensation of hexamethylene diamine and adipic acid. If we are taking n number of molecules of hexamethylene diamine and n number of adipic acid, so we will get the polymer like this. Here we can see this is the condensation. Here the condensation is occurring at this bond. This is the amide. CONH is amide group. So we get amide linkage here. We can see this is the formation of polymer. Now, as the hexamethyl diamine also consists of NH group at the terminal. So again, from this end, we have the polymerization, and the similar way adipic acid consists of COOH group at the terminal position. So we will get condensation from here as well. So this is the simple representation of a polymer. By showing it 2 units only, we can represent a polymer. We don't need to write the whole structure of the polymer. We just need the structure of monomers, and we can draw the structure of polymer from that on. So on the basis of mode of preparation, we have 2 type of polymers, addition polymers and condensation polymers. In addition polymers, we must have double or triple bond in the monomeric unit, where in condensation polymers, we must have functional group in the monomeric unit. Moving on to the next classification. This next classification is based on the mechanism of polymerization. So mechanism of polymerization. So we have 2 types of mechanism here. One is known as chain growth polymerization. What happens in chain growth polymerization? Basically, we form the addition polymers by the chain growth polymerization. Addition polymers are chain growth polymers. Chain growth polymerization takes place by free radical mechanism. What we have? Free radical mechanism we have to do. So we will produce a free radical and then proceed the polymerization. So free radical mechanism or addition polymerization occurs in 3 steps. The first step is known as initiation step. In the initiation step, what we take? We would take benzoyl peroxide. We have taken benzoyl peroxide. This is how the structure of benzoyl peroxide looks like. C6H5CO O O CO C6H5. So the homolytic fission will occur by peroxide linkage here, and this bond will break, giving 1 electron to each oxygen and forming benzoyl free radical C6H5CO O radical is formed. Two molecules of benzoyl free radical will form, and this molecule is unstable. So what happens next? The radical will move here, and the C bond will break again in homolytic fashion. So we will get a radical on the phenyl group. Okay, from here, carbon dioxide will be removed as the product, side product, and we will get C6H5 radical. This is known as phenyl radical. This one we get as a phenyl radical. So in the initiation step, first we are initiating the reaction by the homolytic fission of benzoyl peroxide and getting phenyl free radical. Now phenyl free radical attack on the desired monomeric unit. Here we have to take ethene as the unit. So we are preparing basically polyethene. So now this C6H5 will attack on the CH2 bond, CH2 having radical. So basically what happens, the breaking of double bond will occur in the homolytic fashion. So basically what we get, we will simply get C6H5 will be there. This attack occurs simultaneously. So I am showing you how it occurs by taking radicals. So now what we can do? We can form the bond between these two radicals, and we will get C6H5 CH2 radical. So this is how chain initiation steps occur. We will get C6H5 CH2 radical, and now as this radical forms, the propagation step will occur. Chain will propagate. That means the propagation of chain will occur. That means chain lengthening will occur. So C6H5 CH2 radical will attack on the another molecule of ethene monomer, and we get chain lengthening. So what we have C6H5 CH2 radical, and it will react with CH2. So again, reaction will occur here. So homolytic fission of bond will occur, and we will get C6H5 CH2 radical. We will get C6H5 CH2 radical, and the reaction will going so on. So we will do the same process until all the molecules consumed. Like we are having n molecules of ethene here, so we have got polyethene, but we also have the radical. So our next step is to terminate the chain. That means to stop the reaction. So to stop the reaction, what will happen? Chain termination step will occur, and we do have so many molecules, so many radicals. So we combine the two radicals and chain will terminate. So like this, we have taken two chains of C6H5 CH2N CH2 radical, and again C6H5 CH2N and CH2 radical. So these two radical will join together and will give us a polymer of polyethene. So this is how polymerization of polyethene will occur. So first step is the chain growth step. First type of polymerization based on the mode of preparation is chain growth polymerization. In this, addition polymers are formed. Addition polymers are formed by the polymerization. So we have taken free radical mechanism. In free radical mechanism, we produce a free radical that initiate the reaction and attack on the monomeric unit. So here we are preparing polyethylene. So we have taken monomer as ethene. So phenyl free radical, which is produced by the benzoyl peroxide, will attack on the ethene, and we will get C6H5 CH2 radical. Now, next step is to propagate the chain, to lengthening the chain. So in that, we have taken more number of monomeric unit, and as the radical is already there, so it will attack on the monomer, and step growth will occur. Growth will occur of the chain. And finally, we combine the two chains to terminate the reaction or to stop the reaction. So two radicals combine together and produce polyethylene as the product. So this is the first classification. Next, we have step growth or condensation polymerization. Basically, here we produce the condensation polymers by the step growth method. Here, one step will occur one by one. Here, the examples are nylon 66 and terylene. Again, hexamethylene diamine. What is hexamethylene diamine exactly? You can write it like this as well. H2N H2N CH2 6 NH2. We have taken this is known as, due to 6 carbon, this is methylene diamine. And next one is adipic acid. Adipic acid is COOH CH2 4 COOH. It is basically hexane 1,6 dioic acid. COOH CH2 4 COOH is basically hexane 1,6 dioic acid. Now, what happens? Basically, we have NH2 group. From NH2 group, we take one hydrogen atom, and from carboxylic group, we take OH. C double bond O. So these two groups combines and will produce NHCO. So we get amide. So that's why this type of polymer are also known as polyamide, in which the major structure, the polymer consists of the amide chain. They are also known as polyamide. So in condensation polymer, there is always removal of a small molecule. So in a similar manner, step growth polymerization is used to produce the condensation polymers. So small molecule will be removed and we get desired polymer as nylon 66. This polymer is nylon 66. We get nylon 66 as the polymer. Moving on to the next, we have two types of polymers again based on the types of monomeric unit, like homopolymer and copolymer. In homopolymer, what we get? We have the same repeating unit, polymers in which repeating structure unit derived from the only one type of monomeric unit. That means you will have only one type of monomeric unit. So that type of polymers are termed as homopolymer. When we have only one type of monomeric unit, those polymers are termed as homopolymer. Examples are here: polyethylene, polyvinyl chloride, polyisoprene, neoprene, polychloroprene, polyacrylonitrile, PAN, nylon 6, polybutadiene, Teflon, cellulose, starch, glycogen. These are the example of homopolymer. These polymers are made by only one type of monomeric unit. We are also going to discuss their structure later on this. So here is the example. We have taken ethene and we have get polyethene. So in polyethene, all the units are monomeric unit are ethene. So that's why it is called as homopolymer. Then we have copolymers. In copolymers, the repeating structure unit derived from two or more types of monomer unit. That means we will have two different types of monomer. That polymer is known as copolymer if we have two different type of monomer. Here example is nylon 6s, terylene, bakelite, glyptal, buna S, buna N are some of the example. For example, if we take nylon 6,6, so it is made by hexamethylene diamine and adipic acid. So based on the type of monomer, we have two types of polymers, homopolymer and copolymer. Homopolymer are made by the same repeating unit, repeating monomer, and copolymer are made by at least two and more than two type of monomer unit. So next classification based on the type of forces, molecular forces. The next classification is based on the molecular forces among the monomeric unit to produce a polymer. So the polymer will have a particular intermolecular force of interaction. So on that basis, we have different types of polymer. First is elastomers. So elastomers are basically rubber-like solid with elastic properties. That means stretching. So in these elastomeric polymer, the polymer chain are held together by the weakest intermolecular force. So elastomers are basically stretchable. Why they are stretchable? Due to weak intermolecular forces in between them. Examples are buna S, buna N, neoprene. So elastomers in the polymers which have the weakest intermolecular forces are known as elastomers. Next, we have fibers. So in fibers are the thread forming solid which possess high tensile strength and high modulus. Polymers in which the intermolecular forces of attraction are strongest and are called fibers. So in fibers, basically they are thread forming solid which possess high tensile strength and high modulus. Polymers in which the intermolecular forces of attraction are the strongest are called fibers. These forces are either due to the hydrogen bonding or dipole-dipole moment. So if a polymer possesses hydrogen bonding and or dipole-dipole interaction, the molecular forces will increase and they have high molecular forces due to which their tensile strength will increase. Examples are polyamides. In polyamides, intermolecular forces are due to hydrogen bonding, while in polyester, terylene and dacron, and polyacrylonitrile or lone, the dipole-dipole interaction is there between the polar carbonyl group and the polar carbonyl group and the cyano group respectively. So if we are talking about polyester, so there is in polyester we have this kind of structure COO. So there is formation, there will be a dipole form and this dipole will interact with another dipole, and in polyacrylonitrile we have CN. So here again a dipole will form. So due to this, we have dipole-dipole interaction in between the fibers. So they have the high tensile strength, and high intermolecular forces of interaction. Examples are polyamides, polyesters. So as we have discussed, because of in polyamides we have CON, dipole hydrogen bonding, and polyester we have dipole-dipole interaction. Next we have thermoplastics. Thermoplastic are linear or slightly branched long chain molecules capable of repeating, softening on heating, and hardening or cooling. So basically thermoplastic, when we heat them, they become soft, and when we cool them, they become hard. So those type of polymers are known as thermoplastic. These polymers possess intermolecular forces of attraction intermediate between elastomer and fibers. So the forces are not very high than the fibers and not very low than the elastomers. They have some intermediate forces or intermolecular forces. Those type of polymers are termed as thermoplastics. Examples are polyethylene, polystyrenes, and polyvinyls are the example of thermoplastics. Now we have thermosetting polymers. In thermosetting polymers, they are cross-linked or heavily branched molecule which on heating undergo extensive cross-linking in molds and again become infusible. So basically, if we heat the thermoplastic, they give the cross-linking molds and cannot be reused again, because we can only change their shape only once on heating. And when we cool them, they will get a fixed shape, and on again heating, there will be no effect. So in thermosetting plastic, they can be molded only once. We cannot reuse them, as they cannot be change their shape on heating and cooling simultaneously. Their example is like bakelite, urea, formaldehyde resin are the example of thermosetting polymers. So on the basis of molecular forces, intermolecular forces, we have 4 types of polymers: elastomers, which have the weakest intermolecular forces. Then we have fibers that have the highest intermolecular forces due to hydrogen bonding and dipole interaction. Next, we have thermoplastic, which on repeatedly heat become soft and hard on cooling. And then we have thermosetting polymers, which become hard on heating and cannot be molded again into the other shapes. So we cannot use them. Now, we have biodegradable polymer as well. So biodegradable polymers are those polymers which basically when came into the contact or leave with the nature, degrade eventually. A large number of polymers are quite resistant to the environment degradation process and are thus responsible for the accumulation of polymeric solid waste material. So basically, as you have heard of, like plastics are causing pollution in. Why? Because they are non-biodegradable. So most of the polymer and are the non-biodegradable, and they create polymeric waste, like in seawater, it's getting polluted due to the non-biodegradable plastic. So the large number of polymers are responsible for that hazard. Now, these solid waste pose acute environmental problem and remain undegraded for quite a long time. So these polymer doesn't get degrade and have the acute environmental problem due to non-biodegradable nature of these polymers. In view of general awareness and concern for the problem created by the polymeric solid waste, certain new biodegradable synthetic polymer have been designed and developed. So now, what have scientists have done? Due to these problems, non-biodegradable nature of polymers, they have produced some polymers which are biodegradable by making changes into them. So that is the general awareness and the concern for the problem created by the polymeric solid waste. Scientists have developed new type of polymers which are biodegradable. These polymers contain functional groups similar to the function group present in the biopolymer. So biopolymers are basically a biodegradable polymer, like which are occurs in nature. So scientists have developed polymers similar to the biopolymers. Examples we can discuss: aliphatic polyester are one of the important class of biodegradable polymers. So basically aliphatic polyesters, the examples here we can discuss, which is poly beta hydroxy butyrate, co beta hydroxyvalerate, PHBV. So this is the polyester which is biodegradable. It is obtained by the copolymerization of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. When we copolymerize 3-hydroxybutanoic acid and 3-hydroxypentanoic acid, we get PHBV, and it is used in specialty is packaging, orthopedic devices, and in controlled release of drugs. PHBV undergo bacterial degradation in environment, so that's why it is biodegradable polymer. The examples, the PHBV structure look like this. We have taken 3-hydroxybutanoic acid. On third position we have OH, so this is 3-hydroxybutanoic acid, and secondly we have taken 3-hydroxypentanoic acid. So butanoic acid and pentanoic acid. Now what we have done, we have basically the structure is look like this. So I can write 3-hydroxybutanoic acid like this, C double bond O, OH. We have CH2, CH, OH here, and I'm writing CH. In this similar manner, I am writing 3-hydroxypentanoic acid. So we need OH in front of COH for the formation of ester. So we take OH, and here 2 carbons are there, so we can write them as C2H5. CH, CH2, COOH. Now polymerization will occur and water will remove, as it is a condensation polymerization, and again from this end again we will have COOH group. So H will remove from here, and from here OH will remove. So basically what we will get O, CH, CH3, CH2, C double bond O, O, CH, C2H5, and then CH2, C double bond O, and this will end here. So we get this as a polymer. PHBV is the class of biodegradable polymer. Next example is nylon 2 nylon 6 is also a biodegradable polymer. It is an alternating polyamide, like polyamides we have nylon 6,6 and nylon 6. So those polymers are non-biodegradable, and we have produced a polymer which is biodegradable and alternating polyamide. It is made by glycine, an amino acid, and a aminocaproic acid, again a amino acid, and it is biodegradable. So nylon 2 nylon 6 is prepared by the 2 amino acids, glycine and caproic acid. Glycine is the only amino acid with no chiral carbon, so it is optically inactive. That is the extra information. Now, what we have? We have NH2 CH2 COH. This is glycine. NH2 CH2 COOH, glycine. And we have taken NH2 CH2 5 COOH. This is amino caproic acid. Amino caproic acid. So what happens? OH from the carboxylic acid end and H from the NH2 end will remove and we get CONH. This polymer is known as nylon 2, nylon 6. This is the in category of biodegradable polymers. So we have also discussed the biodegradable polymers, PHBV and nylon 2, nylon 6. Now, I will show you some examples and some important polymers. Just wait for a second. Okay, so here we have some important types of polymer, so with their uses. So basically the question will be asked from this table only. You will be asked what is the monomeric unit and what are the uses of that particular polymer. So we can discuss from here. Some common addition polymers and chain growth polymers. So here we have condensation as well as addition polymer both. So I will let you know the mode of preparation as well. So first we have polyethylene. So we have two types of polyethylene. We will discuss it when we get a low density polyethylene and high density polyethylene. We will discuss it later on after discussing this table. So polyethylene is CH2N. The formula is CH2CH2N, and the monomer used is ethylene. CH2 double bond CH2 ethylene is used. So the uses, it is used in the film wrap and plastic bag. Used in the film wrap and plastic bag. This is low density polyethylene. This one is low density polyethylene. Next we have high density polyethylene. High density polyethylene, and high density polyethylene, again the formula will be same as that of low density polyethylene, and monomeric unit is ethylene again. But the uses is it is used in electrical insulation of bottles and toys. So both the polyethylenes, as polyethylene is the addition polymer, they are formed by the addition polymerization. These are the formed by the addition polymerization, both the type of polyethylene. Next we have polypropylene. Polypropylene, also known as PP. So in polypropylene, what we have taken, we have to take a monomeric unit of propene. When we have monomeric unit as propene, so we get polypropylene as the monomer, polypropylene as the polymer. And it is used in the manufacture of ropes, toys, pipes, and fibers. And again, it is formed by the addition polymerization. It is also formed by the addition polymerization. As you can see, it consists of a double bond. We need a double bond or triple bond when we are making addition polymerize. polymers. Next, we have polyvinyl chloride. Polyvinyl chloride, that is known as PVC. In PVC, we need vinyl chloride as the monomer. CH2 double bond CHCl is the monomer, and when we polymerize it, we will get PVC, polyvinyl chloride. It is used in the manufacture of raincoats, handbags, vinyl flooring, water pipes. And again, it is also formed by the addition polymerization. It is also formed by the addition polymerization. Next, we have polyvinylidene chloride. Polyvinylidene chloride, it is known as sarin A. So here in polyvinyl chloride, we have taken only one chlorine. If we have taken two chlorine, it will be known as vinylidene chloride. So in vinyl chloride, we have replaced hydrogen with chlorine. So we get two chlorine. So when we polymerize it, we get sarin A. It is used in the formation of seat covers, films, and fibers. So it is also comes under the addition polymerization. It is also formed by the addition polymerization. Next type of polymer we have polystyrene. Polystyrene or styrene. In polystyrene, what we have taken, the monomer is styrene. So what is styrene basically? When on a benzene, we have CH double bond CH2. So this is known as styrene. So the upper part CH double bond CH2 is there, double bond is there. So it will go under the addition polymerization. Addition polymerization will occur, and polystyrene we will get. It is used in the as a insulator wrapping material. Insulator wrapping material, manufacture of toys, radios, television, cabinet is occurred by the polystyrene. Next, we have polyacrylonitrile. In short, it is also known as PEN, polyacrylonitrile. It is also known as Aldone acrylate. These are the other names of polyacrylonitrile. Here, the monomeric unit is acrylonitrile, CH2CHCN, CH2CHCN, and we get polymer from it. It is used in the rugs, blankets, and clothing material. Next, we have polytetrafluoroethylene, which is known as PTFE, Teflon. PTFE or Teflon. Here we have CF2 double bond CF2. On double bonded carbon, we have replaced all the hydrogen by the fluorine. So it will give you tetrafluoroethylene. It is known as tetrafluoroethylene. So it used in the non-sticky surface of electrical insulation. So here non-sticky utensils are produced by the Teflon. Next we have polymethyl methacrylate. Polymethyl methacrylate. It is also known as PMMA. Polymethyl methacrylate. Lucite, plexiglass, and Perpex are the another name of the polymethyl methacrylate. So here what we have taken? We have taken CH2 bond C and then a methyl group on it and COOCH3. So I can write this structure like this. The structure is basically like this: CH2 double bond C CH3 COOCH3. This is the structure, and when we polymerize it, we get PMMA. It is used in the light covers, sign skylights. Next, we have polyvinyl acetate. And all the polymers are in the category of addition polymerization. Again, this is all, PEN is also addition, PTFE is also addition, PMMA is also addition. Polyvinyl acetate, PVAC. So here the unit is CH2 bond CH OCOCH3. So we can write it structure like this: CH2 CH O CO CH3. This is the structure, and this is known as vinyl acetate. This compound is known as vinyl acetate. It is used in latex paint and adhesive. Now, the important one, natural rubber. We will discuss structure of natural rubber. So it is made by the natural rubber is made by a monomeric unit which is known as isoprene. Isoprene is the monomeric unit in the natural rubber, and it is in the cis form. It is in the cis form, and it requires vulcanization for practical use. That means, what is vulcanization? We will discuss. So we will discuss natural rubber separately later on. Next, we have neoprene. Neoprene is, you can say, synthetic rubber, and it is formed by the chloroprene unit. It is formed by the chloroprene, synthetic rubber, oil resistance, seal, gasket, hoses, and conveyor belt. The use of the synthetic rubber. Next, we have SBR, styrene butadiene rubber. SBR is also known as Buna S. Styrene butadiene rubber, also a synthetic rubber. Here, what we have taken, it is a copolymer. It is a type of copolymer, and this copolymer is formed by the addition polymerization. This is important. This copolymer is formed by the addition polymerization. Both the rubber, synthetic as well as natural, are formed by the addition polymerization and are homopolymer. Both the natural rubber and neoprene are the homopolymer, but SBR, styrene butadiene rubber, Buna S, is copolymer of styrene and butadiene. It is the copolymer of styrene and butadiene. Again, nitrile rubber, which is Buna N, it is also copolymer. It have two different monomer and also addition polymer. Here, it is formed by the acrylonitrile and butadiene. Acrylonitrile and butadiene. So the uses of Buna S are, it is used in the tires, floor tiles, footwear, cable insulation. And the Buna N is used in making oil seals, tank lining, and hoses. Now, condensation polymerization are there. Now, condensation polymerization. So first we have polyester, which is basically Dacron, Terylene, or Mylar. This is the name. So in this we have monomers as terephthalic acid. Terephthalic acid, we can draw this structure like this. On benzene ring, we have to place COOH and COOH at the para position. So it is a para dibenzoic acid. So this is known as terephthalic acid. And ethylene glycol. Ethylene glycol is basically CH2, OH, and OH. So one monomer consists of alcohol and another monomer consists of carboxylic acid. So the condensation of carboxylic acid and alcohol will occur, and we get a condensation polymerization. And the linkage here is ester, so COO. So that's why they are called as polyester. They are used in formation in making fabric and tire cord. Next one is glyptal, or this is also known as alkyl resin, glyptal or alkyl acid. So here again we have taken carboxylic acid and alcohol. Same alcohol we have taken ethylene glycol. This is ethylene glycol, but the carboxylic acid we have taken, that is phthalic acid. What is phthalic acid? So like in terephthalic acid, we have carboxylic acid on para position. Here we will have carboxylic acid on the ortho position. So this is known as phthalic acid In enthalic acid, we get glyptal. The uses are paint and lacquers. Next, we have polyamide. Polyamide nylon 6 is this one we have discussed already. We have to take adipic acid, COOH, CH2COOH, and hexamethylene diamine. So we will get a polyamide. Nylon 6 is a type of polyamide. It is used in parachute and clothing. Fabrics are made by the polyamides. Next, we have nylon 610. So here, what we have taken? We have taken hexamethylene diamine and 1,10 1,10 decane dioic acid is taken. Here in nylon 6, we have 6 carbon, but we are having here total 10 carbons. So 4 carbons are increased. Next is caprolactam. Not caprolactam. Yes, caprolactam polyamide nylon 6. Nylon 6 is also known as Perlon L. The monomer unit is used here is caprolactam, and only one type of monomeric unit is used, so that's why it is known as homopolymer. All the above example are the copolymer, and this one is the homopolymer. It is used in the formation of rope and tire cord. Next, we have bakelite. In bakelite, what we take phenol and formaldehyde in excess. Phenol and formaldehyde in excess. And it is used in the electrical switch, combs, handles of utensils, computer disks, and bowling balls. Bakelite. Next, we have urea formaldehyde resin. Here, the monomers are urea NH2CO NH2 and HCHO formaldehyde. It is used in the making of unbreakable cups and laminated sheets. The next one, we have melamine formaldehyde resin. In melamine formaldehyde resin, we take melamine as the monomer and formaldehyde as the monomer. It is used in the formation of unbreakable crockery. Now, next one is Kevlar, polyamide Kevlar. So, the monomers we have taken here is para-dibenzoic acid, that is terephthalic acid, and para-diaminobenzene. So the structure can be drawn like this. One is terephthalic acid, COOH, monomers, and next unit is NH2. So these are the monomers. It is used in the formation of tires. Polyamide Nomex. And so now we have taken monomers as meta, COOH, and NH2. These are the monomers in the polyamide or Nomex. Polyamide Nomex. Next, we have polyurethane spandex. In this, we have taken ethylene glycol and this compound. On benzene, we have CH3 group and N double bond C double bond O, and it is used in the forms shoes, automobiles, seats, and component. Seat component. Okay, sorry. Last one is polycarbonate lexane. polycarbonate lexane is formed by the bisphenol A, X2CO. X2CO is basically carbonyl. X can be OCH3 or Cl. So you can have a look on this structure. So what we have taken bisphenol. It is like this, C, benzene. Carbon is there. We have two CH3 group on this carbon. Again a benzene ring and a OH. X2CO is C double bond O. Here we can have Cl, Cl or CH3, CH3. So basically what happens, Cl yes, Cl, C double bond O, Cl. HCl will remove from here and we get the polymer. So this compound is specifically used in the bike helmet, goggles, bullets, and bulletproof glass. Lexane. So these are the some example of polymers. Now we will discuss some important polymers like first we will discuss polyethylene. Yes. So we have two types of polyethylene. One is low density polyethylene and another one is high density polyethylene. Just a second. Okay, let's first discuss rubber. So rubbers, we have natural rubber and a synthetic rubber. So natural rubber possesses elastic properties. There are elastic properties in natural rubber. It is also termed as elastomer and has a variety of uses. It is manufactured from rubber's latex, which is a colloidal dispersion of rubber in water. This latex is obtained from the bark of the rubber tree and is found in India, Sri Lanka, Indonesia, Malaysia, and South America. Natural rubber is a linear polymer of isoprene. Isoprene is 2-methyl-1,3-butadiene. So this one, I can do this structure. Butadiene, basically when you have double bond on conjugated butadiene system, you can say carbon, double bond, carbon, double bond, carbon. On 1,3 carbon, you are having double bond. And at second carbon, you are having 1-methyl group. So this will become 2-methyl-1,3-butadiene. This structure is known as isoprene. This is known as isoprene unit. So when we polymerize it, so one bond, this will move like this. So basically, we will get carbon, double bond carbon, bond carbon. And on second carbon, we are having methyl. So in this manner, we get polymer. Now, it can have a cis or trans structure. So these two units, CH2 and CH2, are at the same side. So that's why it is known as cis. Cis polyisoprene. Which is cis polyisoprene, or you can also put it as cis poly-2-methyl-butadiene. Cis polyisoprene or cis poly-2-methyl-butadiene, both are the correct name of the natural rubber. Now, natural rubber possesses elastic property, that means it have a weak intermolecular forces in that. So what we have to do, we have to vulcanize it. So we will discuss the vulcanization of Vulcanization of natural rubber. Vulcanization. So when raw rubber does not possess the characteristics of rubber with which we are familiar, in order to give it strength and elasticity, it is vulcanized. In the vulcanization process, raw rubber is mixed with the small amount of sulfur and heated. Use of external sulfur increase the cross-linking toughness. 13% sulfur is used in rubber bands, and 5% sulfur is used in the tire rubber. So basically what happens, we have this type of a structure of a rubber, like this structure. So when we put sulfur, what happens? Cross-linking will occur like this. Here, cross-linking will occur, due to which rubber will have a high, you can say, high strength, from which we are familiar to, and elasticity. Otherwise, rubber will be very soft. So there is one more thing. The transform of isoprene is known as gutta percha. The transform of isoprene is known as gutta percha. Dentists use it in the filling of teeth. Next one is synthetic rubber. Synthetic rubber is basically, generally we use neoprene or chloroprene. Neoprene is the polymeric name and chloroprene is the monomer, which is used for the formation of neoprene. It is 2-chloro-1,3-butadiene. 2-chloro-1,3-butadiene is basically monomer of the polymer neoprene. So rubber was important. Now I will discuss HDP and LDP. Low density polythene first. Low density polyethylene. LDP, low density polyethylene, LDP. It is obtained by the polymerization of ethene under high pressure. So if we are talking about the preparation, so low density polyethylene, we required high pressure. High pressure from 1000 to 2000 atm. This much is of pressure is required, and temperature ranges from 350 Kelvin to 570 Kelvin, with presence of traces of dioxygen O2, or a peroxide inhibitor. peroxide inhibitor as catalyst. You can say these are the catalysts. And the mechanism of reaction, mechanism is free radical mechanism, free radical based mechanism of low density polythene, which we have discussed in the earlier part of the lecture. It is highly branched. What we got here, it is highly branched. It is highly branched, this type of polyethylene. So basically what we will have straight chains like this and branching in these the properties of low density polythene is basically this chemically inert. It will not react with other substances. Chemically inert. It is tough, but it is also flexible. Poor conductor of electricity. Poor conductor of electricity. So it is used in uses. If we talk about the uses, it is used in the insulation of electrical wires, and it is also used in the formation or manufacture of squeeze bottles, toys, and flexible pipes. Flexible pipes. So this is the all about low density polythene. Moving to the high density polythene. High density polyethylene. In high density polyethylene, it is basically formed by the addition polymerization again in a hydrocarbon solvent, and here catalyst is required. The catalyst is important for the high density polythene. The catalyst is basically triethyl aluminium C2H5 thrice Al triethyl aluminium and titanium tetrachloride TiCl4. Titanium tetrachloride. Combinedly, this is known as Ziegler-Natta catalyst. Ziegler-Natta catalyst. So there can be a question like what catalyst is used in the formation of high density polyethylene? That is Ziegler-Natta catalyst. Pressure is low. Low pressure is required in the range of 6 to 7 atm only. And the temperature ranges from 333 Kelvin to 343 Kelvin. is the temperature range for the high density polythene. And high density polythene is basically consists of linear chains. High density polythene is consist of linear chains like this, simple linear chain. And that's why it is having high density, because in linear chain we can have close packing. Due to those close packing, the density will increase, and whereas in low density, the branching will decrease the uh, density of the polythene. It is also chemically inert. Chemically. Just a second, just wait for a minute. Okay, so high density polythene is also chemically inert. It is also chemically inert. And it is more tough than the low density polythene, more tough and hard. It is used in the uses are in the manufacturing of buckets, dustbin, pipes, etc. So these are the uses of the high density polythene. So we have discussed all the type of polymers now. So now we will move to the questions which are asked in previous year from this chapter. So just wait a minute. Okay. Now we will discuss the types of question which have been asked in the previous year from the polymer chapter in IIT JEE exam. JEE means exam basically. So the first question is, polymer used in Orlon. So we have to name the polymer which is used in the Orlon. So you have been asked the other name of Orlon, simply other name of Orlon. So what is the other name of Orlon? It is polyacrylonitrile, polyethylene, polycarbonate, polyamide, and polyacrylonitrile is given. So correct answer will be polyacrylonitrile. Here we use acrylonitride, CH2 double bond CH, CH. This compound is known as acrylonitrile. The name of this compound is acrylonitrile or vinyl nitrile. So this is the monomeric unit. When we do the polymerization, we will get CH2, CH, CN, and this is known as polyacrylonitrile. In short, we called it as PAN, and the other name of this compound is Orlon. So the correct answer is option 4, Orlon. Next question. Match the list. So we have polymers. Different polymers have been given. Now we have to match the list. First, we have given polymers and their types or class. Types or class. First, we have nylon 2, nylon 6. So nylon 2, nylon 6 is a biodegradable polymer. So we will match it with 2. So A will be 2. We will also check from the options. So in third option, we have 4, and in first option, we have 4. So 1 and 3rd cannot be the answer. In second option and fourth option, we have 2. So answer will be from 2 and 4. Next is Buna N. Buna N. What type of polymer is Buna N? So Buna N and Buna S are the synthetic rubbers. So we will match it with third. Buna N and Buna S are synthetic rubber. So now we have got the answer there, because in second we have BS third and fourth we have BS first. So we have got the answer, but we will confirm it. Like urea formaldehyde resin. Urea formaldehyde resin. So it is a thermosetting polymer. Urea formaldehyde resin is a thermosetting polymer. Dacron. Dacron is polyester. Dacron is the polyester. Okay, moving on the next. We have Buna S can be represented as. So we have to represent Buna S. So in Buna S, we should know the monomers. So the Buna part, you can say, stand for CH2, CH, double bond CH2, butadiene. It is 1,3-butadiene. And S part is from styrene. S part is from styrene. CH, double bond CH2. Now, when we polymerize it, we will get this bond. You can move here. Here will be this bond formation between CH2 and CH. This bond will move here, and here we will have a bond. So the structure will be like this: CH2, CH, double bond, CH, CH2, CH, C6H5, CH2, N. This will be the structure. So now you can check from the options which structure is correct. So in first structure, we cannot have double bond on the first carbon. This is incorrect. So the structure we have drawn is matched with the second structure. So answer is 2. We can put CSC above or below anywhere. We must not have, this is incorrect, and also this is incorrect. So second structure is the correct answer. The next question is, a polymer X consists of linear molecules, linear chain, is closely packed. It is prepared presence of triethyl aluminium propyl and tetrachloride, titanium tetrachloride and trimethyl aluminium. Under the low pressure, the polymer exists. So like they are saying, it is having linear structure, closely packed, in presence of triethyl aluminium and titanium tetrachloride. So this is Ziegler-Natta catalyst. So these properties are matched with the, all the condition match with the high density polythene. High density polythene is prepared by using Ziegler-Natta catalyst, and linear chain consist in high density polythene. Also, this is closely packed. Next is ethane at 3332 to 343 Kelvin and 6 to 7 atm pressure in presence of AlEt3, triethyl aluminium and titanium tetrachloride undergo addition polymerization to give LDP. LDP is low density polythene. Statement 2, caprolactam at 553 and 543 Kelvin in H2O through step growth polymerization to give nylon 6. So we have to mention which statement is true and which statement is false. So here we have given ethane. So I think this must be ethene. This can be ethene. Ethene 3,3,2,4, 3,4,3 and 6,7, and this is Ziegler-Natta catalyst. So we don't get LDP here. We will get HTP. High density polythene will be formed. High density polythene will be formed by using the Ziegler-Natta catalyst and temperature ranges and pressure which is given in 6 to 7 atm. So first statement is false. First statement is absolutely false. Now we have to check the another. Now nylon 6. Nylon 6 we have to prepare. So what is caprolactam? I will draw this structure. C, or just a second, I am drawing the structure here. C double bond O, N, H, and 1, 2, 3, 4, 5, 6, C double bond O, N, H, Yes. So this is the structure of caprolactam. Caprolactam. When we heat it 533 to 543 Kelvin, what happens? This bond will break and we get C double bond O. We are taking N molecules of it. C double bond O. 1, 2, 3, 4, 5 carbons are there. CH2, 5, N, H. This is known as nylon 6. This polymer is known as nylon 6. The name of this polymer is nylon 6. Next, again, we have got a match the following question. We have given some examples and we have to match it with the list type. So 2-chloro-1,3-butadiene. 2-chloro-1,3-butadiene will look like this: carbon, double bond carbon and Cl. So this is 2-chloro-1,3-butadiene. Now, what kind of polymer it will give? Biodegradable, synthetic, polyester, or addition polymers? So this is the chloroprene. This is chloroprene. And chloroprene is used in the formation of synthetic rubber, neoprene, so A will be matched with second. Nylon 2, nylon 6 is a biodegradable polymer. We have discussed this. Polyacrylonitrile PAN, a addition polymer, and dacron is formed by the phenol formaldehyde, terephthalic acid and ethylene glycol. So it is a polyester. So A will match with 2, 3 and 4 cannot be the answer. B is matched with first. So second will be the answer. As in first, B is matched with 4. Moving on to the next question. Again, we have got the match the following. Nylon 6 and then we have a column. Vulcanized rubber, cis 1,4, polyisoprene, polychloroprene. So we have the to match the following. Nylon 6, just we have discussed nylon 6, the monomer we used is caprolactam. So A is matched with third. So third and fourth cannot be the answer. Only 1 and 2 can be the answer. Then we have vulcanized rubber. Vulcanized rubber. So due to vulcanized rubber, what happens? We got the cross-linking in the rubber. In the natural rubber, we get cross-linking. So B will be matched with second. So we have got the answer, which is A. Second will not be the answer. Now cis 1,4 polyisoprene. Cis 1,4 polyisoprene. Okay, let me draw this structure. CH2, C double bond, CH2, CH3, H. And here we have N. So this is the cis configuration, and we have used here 2,2-methyl-1,3-butadiene. That is monomeric unit of natural rubber. So C will match with the first. Polychloroprene is known as neoprene only. In the last question, we have discussed that polychloroprene is neoprene, synthetic rubber. So answer will be the A. Again, we have got the match the following. So last year, match the following questions were there in the exam. Monomer and polymer. We have to match monomer and polymer. So tetrafluoroethene. Tetrafluoroethene is like this: CF2, double bond CF2. And from tetrafluoroethene, we will get polytetrafluoroethene, PTFE, which is also known as Teflon, used in non-stick utensils. So Teflon for tetrafluoroethene will match with Teflon. So second and fourth cannot be the answer. Acrylonitrile will give polyacrylonitrile, which is also known as Orlon. So now third cannot be the answer. So answer we have got, first will be the answer. Now we can match. Caprolactam monomer is nylon 6. In isoprene we get Teflon. In isoprene, not Teflon. Natural rubber, na? Isoprene is natural rubber. So these are the previous year questions from this chapter. So we have discussed the polymers. In polymers, we have discussed the classification of polymers. First, we have understand the polymer definition and then classification of polymers on the basis of various types like source, type of structure, mode of preparation, intermolecular forces, biodegradable, and then we have discussed examples of polymer. So that table is important for you. You can have a look at that table, and most of the question will be asked from that only. And then we have discussed PYQs related to this. So we are done with this chapter. Thank you.